So in previous class we discussed about keyless transposition ciphers. So in this class we'll be discussing keyed transposition ciphers, in which we'll be making use of some key. Right, so how we will use it? Yes, see now what we have done in keyless ciphers. The keyless cipher permute the characters by using writing plain text in one way and reading it in another way. So that is the same thing we did in keyless transposition ciphers. We wrote the given plain text, row by row, and then we read it column by column, right? So that was the technique, for dealing with the uh, enciphering using keyless transposition ciphers. Right, so in keyless transposition ciphers, the permutation was done on the whole plain text to create the whole cipher text. Another method we have is to divide the plain text into group of the predetermined size, which we call as blocks, and then we use a key to permute the characters in each block separately. So this, dividing the plain text into blocks, which we have done earlier also in Hill cipher, in Playfair cipher, we divided the given plain text into pairs or in blocks, and then we deal with it. So here in keyed transposition ciphers also, we'll be dividing the plain text into groups of predetermined size, and then we'll be dealing with those groups, we'll be dealing with those blocks of the plain text which we have created. Right, so how do we use key then with the with this technique? That I'll tell you with the help of an example. So here you can see that this is the message which Alice has to send to Bob. Enemy attacks tonight. Right, so the size of the block which will be used for transferring this message will be agreed upon by both the sender and the receiver, and the key size will be the same to that block size which Alice and Bob has decided to go with. Okay, so this whole message will be divided into blocks of the same size. So here in this example, Alice and Bob has agreed upon this block size of 5. So this whole message will be divided into blocks having size 5. So here we can see that this will be the first block. The first 5 characters will be in the first block. The next 5 characters will be in the second block. Then the next 5 characters will be in the next block, right? I guess, okay, this the second block will be up to K, not up to up to C, not up to K. Then the third block will be from K to I. Sorry, this will be up to N, and the last block will be from I to T. Now here in this last block, there are 4 characters left. So we'll be adding one more extra character. Okay, you can add any character X, Z, or any other character for completing this block. So here you can see this is the first block, this is second block, this is third block, and this is fourth block. So here this is an extra character we have added. Now the key used for encryption and decryption is a permutation key. Okay, we'll be using a permuted key for this kind of ciphering technique, which will tell you that how the characters will be permuted. Now this is the key which we have used. Now what does this form of key means? We'll be using this direction for encryption and this direction for decryption. Now what does it mean? It says that here also you can notice that the size of key is equal to the size of block, which is 5, right? So this key tells you that how do you change the positions of the letter of the plain text to create cipher text. So here it says that the third character of the plain text will be the first character of the ciphertext. The first character of plain text will be second character of the ciphertext. The third character will be, the fourth character will be third, fifth character will be fourth, and the second character will be fifth. So we can see from this plain text, we have generated this ciphertext. Okay, so we can check it from here. The third character we have to make as first character in the ciphertext. So here the third character is this one. Okay, so the first character we are having as E. The first character has to be the second character. So this is the first character E. This is the second character in the ciphertext. The fourth character in the plain text, we have to make it the third character in the ciphertext. So this is the fourth character M. We have to make it third character, right? So we will be writing M as the third character. Now the fifth character becomes fourth. So here this Y becomes the fourth character and the second becomes fifth. So this N will be the last character in the ciphertext. Fine. So this is how we encrypt the message using this permuted key, and this thing applies on each and every block we have created out of the plain text. You can check for this also. Here this third character of the plain text is written as first, first has written as second, fourth as this one as third, fifth, which is C, as fourth, and second as the fifth. Okay, so this process goes on until we reach the last block. Fine, so this is how this keyed transposition cipher is used with the help of or implemented with the help of a permuted key. Now next comes the combination of both the approaches. Both means the keyless and the key approach. We can use them combinedly. How do we do this? We will be writing the given plain text row by row first of all. Then we will be using this permuted key, okay, for generating this intermediate matrix, and then we will read it column by column. Okay, so this writing the message row by row and reading it column by column is a part of keyless transposition, and using this permuted key is a part of keyed transposition. So we'll be using it like this. Right, but while decrypting, we cannot use this key which is given. We cannot use this key in the same order which we have used for encrypting the message. So we have to change the position of the letters in the key. Now, how do we do that? Here before that you need to see it that for decrypting end we will be writing the message column by column first of all, and then after decrypting it we'll be reading it row by row. Fine, so this is how we combine these two approaches. Now how do we use this permuted key at the decrypting end? Now you see, this is the encryption key we'll be using for encrypting the message, and the decryption key you can see over here, the characters or the letters or the numbers which we are using in this are same, but they are at different positions. Okay, so how do we decide that which key is to be used for decrypting the message which has been encrypted using this permuted key? So this is the way for finding it out. Now this is an example. Okay, so this is the encryption key which has been used. So we'll be simply writing the encryption key and the corresponding position on which these letters will be there in the ciphertext. Then we'll be swapping this thing and these values. Okay, so these values will be written at the down position, and these values will be written at the this upper position. Okay, so we have simply swapped these values. Fine. So after swapping it, what we will do is we will be sorting these entries. How we will sort it? This pair will be the first one while sorting it. Okay, so it will be the first one, then this will be the second. So we are sorting it on the basis of these values because these values are already sorted. Fine. So and we will move them pair wise. Okay, so this 4 is with 1, so we'll be moving this pair to the first position. So here you can see it is here, this pair is here, then the pair having this entry as 3, it is here. For 4, this pair is at 4th position. Then for 5th we have it over here. For 6th we have it, which is 2 and 6. Okay, and 7th we have 6 and 7. So this is this is the last pair. Okay, so these are the values here. These are the values we'll be using as permuted key at the decrypting end. So this is how we inverse the key in transposition cipher. This process is called key inversion in transposition cipher. Okay, so because if we'll be using this thing at the decrypting end as well, then there will be a problem. So I'll tell you with the example also. Say for example, here we have this message with us. Okay, and if I apply this particular key which I have used for encryption over this, then the result will be something else. So it says the third column will have to be the first column. Okay, so this is the third column. Okay, and you are supposed to make it as first column, which is, you can see over here, this is completely different. So this column cannot be the first column, right? Because your if you do this, your message, the plain text which you are getting over here will be something else. Fine. So this is how we'll be using the permuted key for enciphering and deciphering the message. We can combine these two approaches also, which are keyless and keyed transposition cipher. Okay. Now next thing comes is stream and block ciphers. Now we have covered these two topics, along with the various ciphering techniques which we have studied so far. Uh, so broadly, this symmetric key cryptography can be categorized into these two categories, which are stream ciphers and block ciphers. So under monoalphabetic techniques and polyalphabetic techniques, which we have discussed so far, there are many ciphering techniques which comes under stream ciphers, and many ciphering techniques which comes under block ciphers. So how do we differentiate them? Whenever we have used group of plain text for encryption and decryption process, then those kind of techniques, they come under block cipher. Okay, and whenever we have used the stream of key, or we have dealt with individual characters of the plain text using the stream of key, in that stream the value of key could be same or different, but we have dealt with each character in the plain text separately. Fine, so those kind of ciphers are stream cipher. Okay, so these are broad categories of the symmetric ciphers. Fine. So this is just a representation of it. So if we have a plain text stream P and cipher text stream C and the key stream K, then while using this stream cipher, we'll be dealing with each character separately using this key stream. So in this key stream, these values of key can be same or different. Okay, just like in additive cipher we have used the same value of key for each and every character of the plain text, and in say Vignier cipher we used this key of size m, but all the characters in this key were different. Fine. So but what size of the plain text you are dealing with at one time, so that decides whether that cipher is stream cipher or block cipher. Okay, so we have dealt with a single character of the plain text in additive cipher, in monoalphabetic substitution, in Vignier cipher. So these kind of ciphers, they come under stream cipher category. Okay, and this Playfair cipher and Hill cipher, these kind of ciphers in which we made pairs from the plain text and then we dealt with them. So those ciphers are block ciphers. Fine. So yes, these are some examples which you can go through these additive cipher. So this is the same thing written over here which I was telling you कि additive cipher में हम कैसे we take it under stream cipher. The monoalphabetic substitution is also a type under stream cipher. Here you can also see I was telling you that the values in the key stream are same for additive cipher. Okay, because we use only one value of the key. So each and every value is k over here. In monoalphabetic substitution, we have a separate substitute for or a different substitute for each and every character, and that table is given beforehand. Okay, in Vignier cipher as well, we do not create pairs of the plain text, but we use this key repeatedly for the plain text. But at a time, we deal with only one character of the plain text. Right, so these ciphering techniques which we have, all of these techniques which we have discussed so far, some of them come under stream ciphering techniques and some of them come under block ciphering technique. So you just have to check whether you are dealing with a single character or a group of characters in one go. Okay, so this is the block cipher, right? So here in this you have a group of plain text symbol of size m where m is greater than 1. Okay, and they are encrypted together which create a cipher text of the same size. Fine. So here you can see we have created groups of 3 characters and we are dealing with one group at a time. Okay, and the size of key over here is 3. The size of key block is 3. Okay, so this is block cipher. So as I told you, this Playfair cipher and Hill cipher, they are examples of block ciphering techniques. Okay, so after this, we'll be discussing some algorithms for encrypting the message. Okay, and for understanding those algorithms, we will again cover some mathematics before because without discussing that part of mathematics, you will not be able to understand the algorithms which we'll be discussing. Okay. So these are some things, some of the topics which we'll be discussing under this mathematics part, okay, for understanding the algorithms which we'll be discussing in the coming classes. Okay, so why are we discussing this mathematics now? Because we'll be dealing with the sets, okay, and uh, will be performing some operations on the given set, right? So we have to understand how do we perform those operations on the given set. So this thing will may make you familiar with all those operations and the concept of sets which we will be using. Right, so it says that cryptography requires this sets of integers and specific operations that are defined for those sets. The combination of the set and the operations that are applied to the elements of the set is called an algebraic structure. Okay, so under this algebraic structure, we'll be discussing these three structure, which is groups, rings, and fields. So first of all, we'll be discussing groups. Okay, so this is again the representation of the algebraic structures. Okay, so now we will be discussing that what are these groups and when do we say that a given set is a group or not. Okay, so we can combine two elements of the set to obtain a third element of the set. So we'll be operating on the set, right? We'll be performing operations on the given set elements, right? And these operations which we'll be performing, they are subject to specific rules, and these rules will define the nature of the set. On the basis of these rules, we'll be deciding whether the given set is a group, is a ring, or a field. Fine. So first of all, we'll be covering this, the set which can be a group. So a group is a set of elements with a binary operation which we represent with this a dot. Okay. So the group with a set of element and a binary operation, the both of these things, the group name and the set of operation, we represent it like this. Okay, so this is the name of group and this is a set of operations which can be applied on this group. Okay, so when do we call this set of element with this set of binary operations a group? If it satisfies the four properties, or we can also call these properties as axioms. Okay, so if it satisfies the four properties which we'll be discussing in the next slide, then we say that this given set of element is a group. If it does not satisfy any of the property, then we say that the given set of element is not a group. Okay, now this operator can be any binary operator. It could be addition, multiplication, or any other mathematical operator. Okay, but the elements of this group must satisfy the conditions or the properties, the four properties which we'll be discussing to be called as a group. Fine. So a group can have a finite number of elements or infinite number of elements. So if it has finite number of elements, we call it a finite group. If it has infinite number of elements, we call it infinite group. Okay, this about this commutative group, I'll tell you later. Okay, so before that, we'll be discussing these properties. So these are the properties. The four properties which we were talking in the previous slide are this closure, associativity, existence of identity, and existence of inverse. Okay, this is the fifth property which we'll be talking about. Fine. So if you're given a set of elements and the elements in that set along with the binary operation which is specified with that set, if those elements they satisfy these four properties: closure, associativity, existence of identity, and existence of inverse, then we say that set of element is a group. Okay, so we represent the set like this and the operation like this. Okay, we give the any name to this set. If it is a group, we call it G. Okay, and we write these operation like this and this whole set like this. This dot can be addition, multiplication, division, or any other mathematical operator. Okay, so this commutative property is if any group satisfies this commutative property as well, then we call that group as commutative group. Okay, we call it abelian group also. Okay, so for property they are compulsory to be satisfied, but in addition any group is satisfying this commutative property as well, then we call it a commutative group. Okay, but those four properties must be satisfied. Okay, this is an additional property. If any group satisfies this commutativity, then we say that group is an abelian group. So there is a specific name for these kind of groups, right? Okay, so this is and these are the properties and the meaning of these properties. So closure says that if A and B belong to G, these are the elements in the G, right? G is the group. So if A and B belong to G, then A dot B, this is again the binary operation, we are representing it with dot. Okay, then A dot B is also in G. Fine. So say for example, uh, if I take two numbers 2 and 3, okay, and the operation I am having is this addition operation. This dot operation is the addition addition operation. So what does this property say? That if I perform 2 plus 3, which gives you 5. Okay, so along with 2 and 3, 5 must be there in the group. Sorry, okay, or you can say in the given set. Okay, so it says that if A and B belongs to G, then A dot B is also in G. Now associativity says, uh, say the operation when you perform on A and B first and then on C, it must be equivalent to when you perform the operation on B and C first and then on A. Fine. So say for example, if I take these three numbers 2, 3 and 4. So and the operation is addition operation. Okay. So 2 plus 3, take a multiplication for this because addition will be, obviously it will be same. 2 multiplied by 3 into 4. Okay. It must be equal to 2 multiplied by 3 multiplied by 4. Okay, so the both of these value will give you 24. Both of these expression will give you value 24, right? So they are equal. So we can say that the elements 2, 3 and 4, they are associative. Fine. Next is existence of identity. So it says that there is an element E in the set such that E binary operation A is equal to A binary operation E is equal to A. Now, for example, if we take this addition operation, then when this condition will get satisfied? When we add 0 to any given number. Say for example, the given number is 3, the value of A is 3. So 0 plus 3 and 3 plus 0 will be equal to 3 only. Okay, so this is this property of existence of identity. Now next is the existence of inverse. Now when you apply this binary operation on the on the element and its inverse, then it should give you this element E, okay, which is the identity element. Okay, so here in this case, if you say 3, if you take 3 as an example, so its additive inverse will be -3. Okay, 3 plus -3, it gives you 0. Okay, so this E was 0 for it. Here we have used this 0, so again you are getting 0. Okay, so that means the inverse of the given element exists in the set. right? The last property, which was the fifth property, okay, which makes a set commutative, is called commutativity. It says that A binary operation B must be equal to B binary operation A. So here it is written, which I was telling you, that the groups which satisfy this property, we call those groups as abelian groups, right? So these are the properties which the element of the given set must satisfy to be called as a group. Now this is again the same thing, the application, the operations which I have already shown you. If you have this set of integers and the operation is the addition operation, then we can say that this will be a commutative group as well. Okay, so we can perform addition and subtraction on the elements of this set without moving out of the set. So the result which you are getting after performing the operation, the results must also be in the set, okay, which it was the condition over here as well, and initially also we discussed about it. Okay, so it is saying that we combine two elements of the set to obtain a third element of the set. So the operation, after applying the operation on the elements, the result which you are getting, that result must be in the group as well, in the set as well. Okay, so that's all. We'll be discussing some the kind of or not the kind, actually, some more topics in the group, like what is order of a group, and what are subgroups, and what are cyclic groups. So these some more topics which are related to groups will be discussing in the next class. Okay.